All right, welcome back everybody to episode 29 of Uncertainty and Probability Theory, the Logic of Science. I haven't fixed the lighting problem yet. As you can see, I'm working on it. Today we don't need the board that much, so it won't really make that much of a difference. The homework is going to be anyway to read and understand. There's not much, well, maybe I'll give you some ideas in the homework notes or something that you could do. You could look things up. And you can see how much these things I'm going to talk about are used in real life. So, nothing has a distribution. You'll read all kinds of probability and statistics literature about things having a distribution. They'll say things like X is normally distributed, or gamma distributed, or the underlying distribution is binomial, or the true distribution of these observables is this and such. All of that is false. All of that is absolutely false. Nothing has a distribution. And why? Because a distribution just means the probability of several things that can happen stated at the same time. I'll go over this. And we already know that things do not have a probability. If things do not have a probability, they cannot have a distribution. So it is always wrong to say things like this. And we'll also learn the term random variable. You'll see that one all the time. X is a propositional stand-in, a propositional variable. X is a random variable. There are no such things as random variables. There are propositions, the values of which we do not know or are uncertain based on given evidence that we assume, and other propositions we do know based on other evidence that we assume. So, for instance, you'll see this all the time. They'll say height is normally distributed, or whatever, income is log normally distributed, and all these kinds of things. No. All of those will turn out to be nothing but models. Now, we're not going to really cover models today. We haven't reached the point where we can understand exactly what models are, but we'll hint at it a little bit today. Because all along we've been doing modeling. All along, every probability statement that we make is a model. It takes a list of assumptions, premises, observations, whatever we like, all that stuff we stick on the right-hand side that all go into this X. That's our paradigm. And this is the proposition that we want to know. This is just a schematic of all probabilities. This is the probability of Y, whatever Y might be. It might be a numerical thing like the height of somebody or their income or their grade point. We use grade point average for an example right here. And this is everything we might say, we assume is probative. We assume it's true. Everything on the right of this bar, you'll remember, we assume is true. Doesn't matter if it isn't true. We could still calculate the probability of Y based on this. This is the beauty of this system, logical probability. It's the same thing in any logical equations. We can have any logical set, syllogisms and so forth based on false premises. We can see what we can deduce or not from them. So that's no limitation. All right. Now, the problem with the thinking about things that having a probability, we discussed this many times, is there must be something out there in the world that is causing probabilities or causing observables to take the values that we measure and causes them to be what they are based on this probability, which is either an active cause or it's a property that can be operated on by active causes. And I gave the examples. We could suppose if we say that X, whatever X is, has a true distribution. So here's all the possible values of X. X can be this value, all these different values here. And this is something like the probability over here. Higher levels are more probable and lower levels are less probable. We could say something like this. So if we observe, if we in fact measure an X over here, it's as if, we talked about this last week, there's a restorative force out there that realizes we've caused a value of X very low. It's kind of probable, but we don't have other values over here. So if there's a true distribution, there has to be something that's causing, the next one's going to be maybe somewhere up here. And X prime will measure up here because we got to keep this distributional shape. After all, we're saying it's the true distribution. So there has to be causes out there that are making this kind of a thing happen. And they have to be causes that are probabilistic in some way or another. And none of that makes any sense because there is no causal force out there that could be put in terms of probability. There's no probability field. There's no probability property that nature can operate on by some other measure. There's just things, and things have causes, and we're going to discuss causality in quite some depth, because what we really need is a better metaphysics. And we cannot just think of things in terms of efficient causes. That has led more people astray in science than anything else, I think. That's why we see, like, what's that woman's name? Sabine Hassenpfeffer or something. She says, recent video, you know, science is broken, like I've been saying, or science is stalled. For the last 50 years in physics, they've been working on the standard model, quantum field theory and the like. And why? Because they have abandoned a metaphysics that they should re-embrace. And we're going to talk about all that kind of stuff as we come back to the things. Okay, so nothing has a distribution. You'll see this all the time, though. And maybe I'll just have you look all this kind of stuff up. We can, however, make statements as if things have distributions. There's nothing in the world wrong with that. So, for instance, I could say I'm going to use a normal distribution. Now, remember, 2 or 3 or 4 lectures back, we discovered the normal distribution is an approximation to an approximation. It's a mathematically valid approximation to an approximation of observables. Nothing wrong in the world of using it as long as we remember that it's just a numerical approximation. It's very darn useful, and it's a pretty accurate approximation in some senses. In other senses, what we're going to see here in a second, it's not accurate at all. So we might say, given some list of premises, I'll just call it n. We're going to use a normal distribution, and we're going to say the uncertainty in x is quantified by a normal distribution of some kind. I could state that. I could absolutely state that. So I could say the probability that x takes some little value of x given normal equals something. And for any x, any little x, in from minus infinity to plus infinity, the answer is always going to be 0. The problem is a normal distribution lives on the continuum, and in any slice, any particular number is one out of not just a countable infinity of numbers, but an uncountable infinity of numbers. An infinity of numbers that is much larger than just 1, 2, 3, 4, 5, all the way up to infinity. A number that is much, much larger. So the probability of seeing any number in any of these distributions that we use, these on the continuum, distributions that live on the continuum, is always going to be 0. But of course, in real life, we always measure actual numbers. So nothing can have a normal distribution. They just don't exist. All you can do is posit, well, it's not a normal distribution for the set of numbers we have in front of us, which is always going to be finite, and not just finite, but discretely measured. We never can measure anything continuously. We can never measure a number, any measurement that we take is always a finite, what's the word I'm after? A finite number of precision. No matter if we're going to measure the height of something, and it doesn't matter what scale you pick, meters, whatever, feet, more civilized units, English units, imperial units, I guess. You can measure it down to you can keep getting smaller and smaller and smaller and smaller, detail on the thing, but you cannot measure it to infinite precision. We're always stuck with finite precision, and of course, we never have an infinite number of anything. So these distributions can only ever be approximate. I'm going to go over this again and again and again, because the idea is that there exists a true, in a lot of the classical work, and almost all of it, either Bayesian or frequentist, they think this normal distribution somehow exists. A true distribution exists. And a normal distribution we'll talk about later has certain parameters that give it this particular shape. And those parameters, therefore, have true values that we can estimate. None of that's true. There's never a normal distribution that is a true distribution of any kind, ever. the best it can ever be is an approximation. Because of this, for one thing, this is absolutely fine as an approximation, even though it doesn't work in real life. We could always make, instead of x, we can make an interval. We could say with the probability of big X being in some interval, and that could be a number greater than 0. We could certainly get away with something like that as an approximation. It could be a very reasonable approximation. But this is assuming, remember, we can't get this stuff backwards. We're assuming this normal distributional shape here because of its mathematical properties are nice and we like to work with it. Perfectly fine, reasonable thing to do. But it doesn't mean it's true. It's something we assume. And there's something called the central limit theorem. We'll talk about that another time. That says, though, if you have numbers of a certain type and you go out to infinity with these numbers, infinity, the distribution of these numbers approaches a normal distribution. Okay, that's true. This is a true theorem. You can prove it. But it has nothing, it doesn't mean your reality is ever going to be normal, because you'll never have an infinite number of anything. You'll never have a true life normal distribution. You just won't. Or any of these continuous distributions. Okay. So let's continue. I went on more than I wanted to do, as I usually do. So let's continue on. So not only do things not have probabilities, and therefore, just to emphasize, so we have, here's the probability axis, if you like, and it'll turn out to be something slightly different called a density, but it's all the same. And here's the possible values that our observable can take, or it doesn't even have to be observable, but in science it's always something like an observable. And we draw a shape like this. It's the probability x takes this value is this. The probability x takes this value is this, and so on. We have more than one possible value, and the probability based on some evidence, x equals x given evidence, can be this shape. We could draw this curve. That's not to say that x has this distribution. We assume this distribution to begin with as a mathematical model. It doesn't mean x itself has an inherent property of this distribution, because each of these are probabilities. And we know that nothing has a probability, so nothing can have a distribution. And that means you'll hear it's a very bad abuse of words, English language, particularly because of the normal distribution. You'll hear of x having a mean, or a standard deviation, or variance, or a correlation. You'll hear that x has these things. Well, the word is overloaded. Once again, we can have our fallacies of equivocation. For any given set of numbers, you take, any given set of real numbers that you have, you could always, whatever these numbers are, of course we could calculate a mean of these numbers, and we can calculate a standard deviation of these numbers, or a variance. And if we had two sets of numbers, we could calculate a correlation. That's true. We can absolutely calculate these, but that's not what people mean, or often not what they imply by using these. They say that this mean is this parameter in this normal distribution. For instance, and the standard deviation or variance tells us the width of this shape. So these are the parameters I'm talking about. They'll overload these words, and sometimes they mean the observational, just arithmetic average, perfectly fine, mundane kind of a thing. And they'll equivocate to a non-existent, unmeasurable, unseen, untouchable parameter. I'm going to stress that parameter business enough times in the future that that's enough I'll say about it right here. But they don't exist. You can't touch them. You can't feel them. You can only estimate them. And you'll never know if you're right about your estimation because, of course, they don't exist. All right. So that doesn't apply. That applies to all kinds of things. And you'll hear about time series, for instance. Time series. That's a big one. A big sort of use of things. A time series, has points that look like this, and maybe you can connect the dots. Nothing in the world wrong with this. For some, here's time. and this is the values x right here. And they make a big thing that they say this time series has to be stationary. And by what they mean by stationary is that its properties, things like, there's other properties that we can worry about another time, like its autocorrelation and its mean, are the same at all times. Are the same at all times. Well, you can see it right away that that's not true. I can take the mean, it's not the same as the operational mean, the calculation, the arithmetic average, because of course here's the mean for these 2 points, here's 3 points, that's pretty much the same, here's a 4th point, the mean would now be here, and if we took these 5 points, the mean's going to duck down a little bit. The actual mean is changing all the time, and any function we have of this data is changing all the time. And time series, more than any others, is where you see an enormous amount of abuse of people mistaking their statistical analysis for cause. There are things that are causing each point. And most of the time, for instance, like a temperature or economic index of some kind, or whatever you like that goes through, that's something that has a natural time basis, the number of causes that go into making one of these points be what they are very large, almost always. And we don't know the causes of these just because we can calculate some correlation between these numbers. It's an absurdity. We're taking correlation and assuming it's becoming some kind of causation, which everybody knows is a logical fallacy. But because the math is pretty enough, we think we can get away with it. It doesn't work. Things don't have means. And then you say that, you think, well, I could calculate an arithmetic average. Yes, but that's not what they mean by means. That's the problem with the abuse of terminology that has taken place. Is so it's over a century old now. This type of language, and the words are used in both contexts, and they switch, they equivocate in the same paragraphs, sometimes even in the same sentences. So you got to be extremely careful about that kind of a thing. Okay. Let's work through an example here. It's the same lesson I told us. There was only 2 big lessons that we had to learn in this entire class. And this is one of them right here. This is it. You change the evidence, you change the probability. And probability doesn't exist as the other one. This is it. We're done. Once we learn that, we've got the entire class. Everything can be subsumed under this schematic and logical probability. We don't have to do testing, we don't have to do estimation, we don't have to do anything. Everything fits in this schema, and it works beautifully. Well, that is to say, I mean, there might be lots and lots of math to bring us from this point to this point, and all that kind of a thing, no problem. We'll do that math, but we don't need all that other apparatus that exists. So let me give you an example. So I'm going to use grade point as an example. I think I used Sally. She takes a number of classes. I don't know how many she's going to take. Some number of classes. And it's going to be graded on a point scale. Whatever that happens to be. S-C-A-L-E. Spelling does not count. Some point scale. And we know this class's number is fixed. And we know the point scale, whatever it's going to be. Some universities have A pluses or something, I guess. Doesn't everybody just get A's anyway? So what's the point of this? But back in the old days anyway, people would get grades other than A's. And so there's a scale. Now that implies, if you follow me, all the possible, we deduce from this, we deduce that the possible grades are G1, G2, and there'll be some Gn. This would be the minimum thing at the number of classes she had, whatever that number is going to be. She has a dozen classes, 12 classes, or she has 10 classes, or just one. Doesn't make any difference. And then she'll have some scale. That implies this is a possibility. This G1 is a possibility. We can observe this G1. So if we go on a 0 to 4 point scale, this number will be 0. But if they don't have a 0 point, they start at some other number like 1, well, that number would be 1. The grade point average is obviously you take all the scaled numbers and you divide them by the number of classes. right? So you take all the observations that you have at the scale and you divide by the number of classes. That's the grade point average. I guess I should say that. So at the end, though, there'll be a discrete set. This will be a discrete set of possibilities. Only knowing she signed up for this many classes, only knowing she signed up for this many classes, and the scale, the grade point scale that is going to be used. Now, from this, we can deduce things like the probability that x, if we let x be our grade point, x equal gi, given, we'll call this information, all this information, we'll call it g. Just all this grade point information, we'll call it g. G is going to be the same as the probability that x equals g, j, given g, where I, doesn't matter if I equals j or not, where I, j equals 1, 2, up to n. Given just g, this is the probability. The probability that she could have any one of these values is equal to this. And because of the symmetry of individual constants, which we've done many times, the probability that x equals gi, given g, is going to be 1 over n. Now that is a true statement. This right here, this statement, the probability that x equals gi, given g is 1 over n, is a true statement, which we have deduced many times before. But it will strike you as a strange statement, because you're going to say, I don't think that's really the case, that she's going to have every possibility in this discrete set, this ordered discrete set. This top one would be if it was a 4 scale, this would be a 4. But not every number, what I really want to emphasize here, maybe I didn't do it well enough, is that this is a discrete set. Not every number in 0 to 4 is a possibility. Not every, if she had one class only, and the possible grades only were 0, 1, 2, 3, 4 on a numerical point scale. These are the only possibilities. She can't get a 1.2. She can't get a 1.0007 or any of the other infinite number of numbers that we could have. She could only have these 5 numbers, and that's it. No more than that. That's what we deduce. And that's our set here. This number grows as the number of classes grows and changes with the point scale, but it's always going to be finite and discrete. I cannot emphasize this stuff enough. And so this statement is true, but it will strike you as odd, as I said, because you're going to think, nah, not every one of these things are equally likely. And what are you doing by saying that? You're not calculating based on this. You're saying, I think this has a true distribution. It doesn't. You're saying something like this. The probability that x equals gi, given g and other info, equals something else. SE for something else. You're adding other info on the right-hand side, and if you change the information, you change the probability. You're perfectly able to do that, but it's a different probability than this. That's why you're thinking this. So some people, what they do, the next step, we're building really our first model right here, is they'll say, okay, this is too complicated, because if she takes a large number of classes over a period of years, how many classes do people take? 5 a semester? I don't even know anymore. 10 a year for 4 years. You got 40 classes. So this number gets quite large. The number in this set, the discrete finite set, they'll still be discrete and finite no matter how many classes she takes. But it's a lot of them, and it's hard to keep track of. It's just, you know, too many to really keep track of. Although with computers these days, it's not really any burden. Back in the old days, when they didn't have computers to do this stuff and they worked out these initial formulas, they had to come up with ways to come up with approximations they could manipulate this stuff with some ease. Now, we could easily create this set just in a couple of lines of code, and we're done. And it doesn't matter how large it is, it's really easy to manipulate. So we can calculate probabilities just like this, right? We don't need to use other information, but some people like to use other information. They'll say, why don't we, here is the scale, G1 to Gn, that's the maximum scale that we could have. And if we have a 4-point scale, no matter how many classes she had, that number will go from 0 to 4. Why don't we use a normal distribution? And so people will find, they'll make the first equivocation mistake. They'll say grade point is normal. Or they'll say grade point, they will say grade point is approximately normal. And what they mean by that is not what you and I mean by that, where we're using it as a nice numerical tool that helps us solve equations with some ease. No, they'll mean that the distribution might not be exactly normal, but it'll look something like it. Still, they'll have a true distribution in mind, which is not the case. And they'll draw a picture like this. Okay. They'll fit a model to this. We haven't discussed any of this, how to do any of that. We're not going to worry about that today. But it does bring up an interesting point here. This is kind of what you're thinking. This is the bell curve used for things like grade point and so forth. Problem with it is, it's always going to be an approximation. All of a sudden, we've introduced that complication with the probability of seeing any particular number is now 0. So we have to talk in terms of intervals and so forth. We can talk in terms of intervals like the interval between G1 and G2, G2 and G3. We could do that, no problem. And that's more or less making this discrete problem into something that's roughly continuous. And if we keep that in mind, it's a wonderful tool. I can't emphasize that enough. I'm not trying to say don't use this. I'm trying to say remember your limitations when you're using it. And it brings up another thing. Because the normal distribution gives probabilities from negative infinity to infinity, we're going to have areas on this which gives probability to impossible events conditioned on G. Given G, the probability of X being greater than Gn, given G, is 0. Or being less than G1, given G, is 0. But using this normal model, we'll get something. It might be trivial. It might be absolutely ignorable for any kind of decisions we want to make. It's so small. But I call this kind of thing, probability leakage. Probability leakage. In other words, we have some deducible truth. G is true, an observed truth about the world. And therefore, with respect to the observed truth about the world, our approximation has some leakage. And most of the time, we're going to talk about this in depth when we talk about modeling. This leakage goes unnoticed and models become ridiculous because of it, because they don't talk in terms of observables. You notice we're talking still in terms of observables here. I'm still trying to calculate the probability of a grade point. That's not what's done in ordinary modeling. They talk in terms of means and true means and confidence intervals and parameters and all this kind of stuff. So we'll talk about all that in time. So the question is, can things have a true model? We're going to talk about this many times too. Yes, things can have a true model, no question about it. This is a true model. This is a true model. It's maybe not a great model, but it is a true model. We've deduced G, and so we deduce these things. This is a true model. There's a saying that's going around, the shorthand version was, it's all models are false, but some models are useful. That statement is itself false. This is a true model. It is a true model. It's not necessarily the best model, however. The best model is always the model that tells you the cause of each and every grade Sally is going to get. Once we know the full cause of anything, we have perfect predictability, and the thing is no longer random. Random only means unpredictable, unknown cause. I give an example in the book, another perfectly valid and true model. So these are all models. Every probability as we've done, these are models. Every probability we've ever done turns out to be a model. That's simple as that. That's again, everything is subsumed under this framework, so we can get away with all this kind of a thing. All right, I think I've hammered that to death, but even still, I feel like I'm rushing this, and I think I've left out a lot of stuff. So you asked me in the questions and everything, and we'll come to it. I'll answer them in the next question. I think, Up next in my book Uncertainty is quantum mechanics. I don't want to hit that yet until we talk about causality. Instead, I think we'll hit back to James and use his chapter 5, which is queer uses of probability, which is a lot of fun. I think that chapter is a lot of fun and sort of emphasizes the details that I'm giving here today in more practical uses. All right, that's it for now. There's more information down below, and be sure to do the homework.